just what I wanted to spend 5 minutes at least pointing you towards. Classical example, now it's not TV sets, but it's different types of plastic in lamps production. So there are 5 groups of data. 6 samples of each type are tested in this example. Strength is measured. So it's more physical measurement, not human perceptual measurement. Companies do all sorts of measurements in their developments. So we can do like this in R. Here the data is put in like this sort of raw way, of course. Classically, you would have data in a separate file, and then you would read the data. That's how it works. There are 2. There is the strength, that's the actual measurements. There is the plastic type, which is the factor, again, that codes for the grouping. Hope you can follow me there. And then the analysis, or first of all, the plot that would give us the box plots would be plot strength versus plastic type. And basically, here's the story about. Here's the full story already, right? Plastic type 2 has the highest strength. 5 has the lowest strength. I mean, it's the medians, but probably the means are the same, more or less the same, right? So don't forget that all what we do is just making sure that if we're going to make these decisions that is so apparent to us, that they're also valid, right? We're not changing the common sense view on the data that you could have before entering this course, that you could have already 10 years ago in your elementary school time. You could have looked at this data. And I mean, I know you were taught box plot back in at least 7th grade. I know for sure. I actually helped my 7th grader with things that I could make exam questions for you on. I've done it, and I get far from 100% correct answers in what you do. I'm sorry, but I'm just sharing this information with you. Maybe I shouldn't. I realize maybe I should, again. ANOVA strength, right? The R output. Is there a difference between the 5 plastic types? Look at this one. Is there a difference between the 5 plastic types? I test the null hypothesis that they're all equal on the mean strength. Are they equal? No, they're not. The p-value is small, right? Very small indeed. So they're not the same. If we use the X table in function in R, we could easily get a LaTeX table like that produced from an output. The X table function works directly on an ANOVA output, so if you run for those that are LaTeXers, you can use the X table directly on the output, and you would get a nicely LaTeX table like this. Anyway, some of you are, some of you are not. So the basic null hypothesis would be rejected. Before we move on, we should just check that everything is okay. Now I just did the stats and I did the F and made the conclusion. I didn't really check that my model thing was okay, right? Let me do some of this. It's a bit in the opposite order, I realized. It's a bit also like in the regression analysis. Sometimes we do model checking in the beginning, maybe we can do model checking at the end, so to speak, to make sure everything is okay. Then if we realize we're not okay, then we shouldn't, of course, use what we've done so far. Then we would have to sort of go back and start all over in given something which is okay, right? That's kind of the philosophy of this. So let's just check and hope things are okay. Yeah, that looks pretty nice. What did I do? I just did. Look at that. I extracted the residual. It's part of the R deal that it can take all the residuals from all the 5 groups, put it into something, and then I applied the QQ norm on those residuals. Oh, and here's a Wally on the non-interactive version. I don't think I would have been able to find that Wally on that. So imagine that you didn't see the red frame again to repeat this. You would have to point at the most deviating one. I'm not sure most of us would have pointed out that one. Maybe some would have been lucky, but I don't think everyone would have. Then we have to tell the story. That's the post hoc. What's the story about this, right? We found the 5 groups are different, and of course the story is in a way what I already saw. That, and here's a way to look at the 5 means. There are different ways to compute 5 means on such data set in R. Here I use the t-apply function, where you tell the y, the factor, and that you want the mean, right? So you get the 5 means, and we get, of course, what we saw on the picture. Type 2 had the highest strength. Type 5 had the lowest strength. Of course, it's just the same thing that I put into the 5 means. Then we could do the post hoc. And now, if you were not told anything about any pre-planned specific comparison, if you don't find that information in what you are reading, in your knowledge of the experiment, of the study, and in a way that reflects real-life applications. If you are a developer at Bang & Olufsen, if you don't find anything, any knowledge in what came before the experiment that we did, if there's nothing to tell me that I was particularly interested in comparing 2 with 5, that was the main purpose of this experiment, a pre-planned comparison. If there is no such information, well, then I don't have a pre-planned thing. If I don't find the information, it's not there, right? So it's a way, until you found that information, you are not doing pre-planned comparisons, right? You are doing just these multiple investigations post hoc. So if we were to do that, we should, in this case, realize that there are among 5 groups 10 possible pairs that we could make, right? So when I do post hoc comparisons, I should use not 5%, but 5 per mil. That's a nice number to use. Dividing the alpha by 10 when I do all those 10 comparisons. The alpha where we would use would be 5 per mil, 0.5% rather than 5%. And here is the thing that you will find the formula. If you look, and I'm not going to dig it out now, if you looked at the confidence interval formula that I gave you on the slide, and you can find in a method box, when there is the same n in all the groups, this confidence width is the same for all comparisons. It had the ni's and the nj's as part of the formula, but if those are the same, this comparison of a confidence, computation of a confidence interval, would be the same for all 10 comparisons, right? It's the same confidence interval. We can use that in a slightly adapted way to find what is known as the LSD, the least significant difference value. That is the width of a confidence interval. The width of a product difference that would just be significant, right? Actually, the width such that 2 means are significantly different from each other. So I can compute this measuring stick, which was on my Bang & Olufsen example in our tool, right? We turn it into a measurement stick such that all means or all pairs of means that differ by more than this error stick, they are significantly different. So we can do all the 10 comparisons in a way like this, because we just have to compute it once. Then, when we have done that, one classic way of reporting the result could be something like this. Look at that. We have a T quantile with the right degrees of freedom, 25, because I had 5 groups of 6 observations in each. That's 30 minus 5, that's 25. Phew. And then we had this LSD, which is basically the confidence interval formula with the square root 2. You can find the method box in the note. And then we take this 4.6. We order the means from smallest to larger to tell the story about the 5 groups, right? Plastic type 5, lowest strength. Plastic type 2, highest strength. I take my measuring stick of 4.61. and I compare the means by the 4.61. Would 5 and 1 be significantly different from each other? Would 5 and 1 be different from each other? Do they differ by more than 4.6? No, they are not significantly different. I put a letter, A and A, to code for the fact the letters A is to help the reader to read off those 10 comparisons. It's a so-called compact letter display. It's not high-tech, it's low-tech visualization, saying that 5 and 1, are they different? No. 5 and 4, are they different? They don't share a letter, so yes, they are different. Or, I see that 5 and 4 differ by more than 4.6, and I have coded that observation into the letter display, right? So the letter display is a coding of all of these, looking of which ones differ by more than 4.6. Of course, you could do that yourself, but now it's coded into the letters, so when you get used to look at the letters, you don't have to think, you can just look at the letters. Sometimes people code by sort of vertical bars also. So we can read off all the comparisons here. That's basically it. Then you've told the story, and your boss will be happy, and hopefully Bang & Olufsen will live forever. Enjoy it. See you over there.